Here's your screencast for section 6.8 to 6.9. 6.8 is on enthalpy of formation, and the learning objective is calculate the enthalpy change for a chemical or physical process based on the standard enthalpies of formation. So the essential knowledge is you want to know about formation reactions. And a formation reaction is when we're producing 1 mole of a compound from the elements. And there's some examples over here. So we're producing 1 mole of CO2 from, and you take the elements in their natural form. So oxygen is a diatomic, carbon is just a solid, their natural form at room temperature. NABR, we're producing 1 mole of NABR, and bromine's a diatomic, so that means we have to take a coefficient of 1/2 in front to cut it down to just 1 atom of bromine, and then you have sodium. And then here's another formation reaction. We're producing C6H12O6, and we just need enough of each element to be able to make that compound. So that's what formation reactions are. We're going from elements in their standard state at room temperature into 1 mole of a compound. And now the next part is we can use the enthalpy of formation, as in how much energy it takes to make these changes happen, to figure out the overall enthalpy change for a reaction. So this is just another way to determine the enthalpy change for a reaction. This equation is on your equation sheet, and it's the sum of the enthalpies of formation for the products minus the sum of the enthalpy of formations for the reactants. So it's products minus reactants. Opposite of bond energies, which that was the last section from yesterday. That was broken minus form, or reactants minus products. Here it's products minus reactants. But this is on your equation sheet, so that should help you remember that. Then the other concept, I'm going to do an example on the next slide, but another concept that you want to know is if you see an element in the reaction, the enthalpy of formation for that is always going to be 0. All right, so here's an example of, we want to find the enthalpy of reaction for this process right here, the combustion of methane. So here's our reaction, and then you would look up these enthalpies of formation. They would be given to you on a table, or there was a table in our textbook that you can look up these numbers. They're always in kilojoules per mole, and you just look these up. So it would be -75 for methane. O2 is an element, so that's going to be 0. CO2 -394, and water would be -284. So then you put those into this equation right here. So the sum of the products minus the sum of the reactants. Here's our products, and here's our reactant. We have a 2 right here because of the coefficient 2 in front of water. So we have to double the enthalpy of formation for water. Okay, and then we just add all those together, subtract that out, and we get our total value right there. And this would be how much energy. It's negative, so that would be how much energy would be released for every mole of methane that reacts. All right, then the last section for Unit 6 is on Hess's Law, and the learning objective is represent a chemical or physical process as a sequence of steps. Explain the relationship between the enthalpy of a chemical or physical process and the sum of the enthalpies of the individual steps. So the essential knowledge is, in Hess's Law, we take several reactions that we know their enthalpy change. We know their delta H. And we want to change them or manipulate them and put them together to equal some unknown reaction. And then what we're trying to do is figure out the enthalpy change for a reaction. So we want to find out delta H for some unknown reaction by putting together several known reactions. And then the key is you want to know, when you manipulate an equation, what does that do to the delta H? So we'll look at that on the next slide. Okay, so here's an example of Hess's law. So this is our unknown equation, as in, well, we know the equation. What's unknown is what's delta H for this reaction. And then we have a series of known equations. So we have these balanced equations, and we already know what their delta H's are. So what we have to do is manipulate these three and put them together to match up with this unknown equation right here. So basically what you do is you look for things, species in this equation that only show up in one of these reactions. And then you have to ask two things. First of all, is it on the correct side? As in, are they both products, or is one a product, one a reactant? If they're on the correct side, then you leave that alone. If they're not, then you flip it so it matches up. The other thing you have to look at is does it have the same coefficient? And if it does, you leave it alone. But if it doesn't, then you multiply by some factor to make them match up. Okay. All right. So here's how we do it. So C3H8 right here. Now this only shows up in the first equation. All right. So we have to make these two match up. So C3H8, it's a reactant in equation 1, but it's a product in our unknown. So then what we have to do is just flip equation 1. So the coefficients are the same, they're both 1. So all we have to do is flip it. Okay, now you have to understand, now when you flip the equation, what do you do to delta H? So flipping the equation means that we change the sign. So we're going to change this from negative 2044 to positive 2044. So if you flip the reaction, you change the sign on delta H. All right. For equation 2, we'd want to look at H2. Because in equation 2, that's the only place where we find H2, hydrogen. So they're both reactants, so they're on the correct side, so we don't have to flip it. But in the unknown, we have a coefficient of 4. This has a coefficient of 2. That means we have to multiply equation 2 by a factor of 2. So the way we manipulate delta H, if we multiply the equation by 2, then you also multiply the delta H value by 2. So this ends up being, once you double it, it's negative 967.2. Okay. Now for reaction 3, carbon is the element. That's how we want to evaluate reaction 3, because this is the only place where we find the element carbon. So in the unknown, we have a coefficient of 3. In equation 3, coefficient of 1. That means we have to multiply reaction 3 by 3, and you do the same thing to the delta H for reaction 3. So this ends up being negative 1180.5. Okay, so you look for things that only show up in one of the unknown, or one of these known equations. Now things like oxygen, water, other species that are found in these equations but aren't in the unknown equation, when you manipulate them and if you put them all together, they would end up canceling out. You'd have the same number on each side, they would cancel out. So all you do is you look for things that only show up in one spot, you make those right, and everything has to work out. Then to get your final answer, to get the unknown delta H, you take the manipulated delta H's and you add them all together, and that's going to be your answer. So delta H for the reaction is going to be 2044 minus 967.2 minus 1180.5, and we end up with negative 103.7. And now remember, put the units back in kilojoules, and it's going to be kilojoules per mole of the C3H8 that's produced. So negative, so it's going to be an exothermic process. And that's how Hess's law works. All right, and that's all for Unit 9. Have a great day. Bye.